Exploitation of IoT ecosystems.
Right. Hello, guys. I'm Fotis, Chantzis. Today we're going to talk about some network exploitation of IoT ecosystems, focusing on mostly protocol vulnerabilities. Just a few things about me. Right now, I'm mostly focusing on assessing medical devices, which basically are a subset of IoT systems. So what we do at work is that we collaborate with a lot of medical device vendors. We bring in the medical devices in our test laboratory. We set it up in the same way as it would be in the production environment. And then we perform a holistic technical security test on it. Mostly gray box testing. So that's why we call it it's neither a penetration test nor a vulnerability assessment. We inspect basically everything from hardware, the network communication, host configuration review, everything you can possibly test in a medical device that is usually also comprised of many hardware components. And my past research has been focusing on network security. I have contributed to the ENMA project, have written the network authentication cracking tool called NCrack. That was part of a Google Summer of Code program back in 2009 and 10. I try to still maintain it when I have free time, but it's not my full-time job. Also done a video course on Nmap. Right now I'm also trying to write kind of a book on IoT exploitation. Again, this is mostly because of my work in the past few years, and also trying to do research on the side. So, as you all know, in IoT, the S stands for security. And of course, there's no S in there. And today we're going to talk about all of these protocols. It's mostly a breadth-first search. We're not going to go in super depth in either of these, but you're going to see a lot of fun stuff that we have managed to do in the past few years. You might not recognize perhaps DICOM. It's mostly a medical healthcare protocol, and we're going to see some interesting things about that later. So why would you research network protocols? I like to mostly focus on the theoretical side. So it's not about just finding vulnerabilities in an implementation, but starting from the inherent functionalities of a protocol. So whenever in the past, for example, when I did the TCP persist timer exploitation, which was basically a bug on TCP itself, not just any implementation. So that's why it spanned so many systems. And basically what you could do with that is that you could take advantage of a mechanism that TCP has to avoid some kind of deadlocks, which is called the TCP persist timer. And abusing that, you could cause a generic denial of service attack in literally almost any server out there that talks TCP, which is basically everything. And the thing is that because that is inherent in TCP, it's not just an implementation bug. It has a bigger impact, first of all. And this, in a similar way, things like the DNS Kaminsky bug from years ago, it was all based on the same principles, that it's not just an implementation thing, but since it's based on the core of the protocol itself, it can be harder to fix. You need a lot of collaboration between all different vendors that implement this protocol. And also sometimes inspecting, the standards, the RFCs, the design of the protocol itself can help you pinpoint specific implementation bugs. And we're going to see an example about that on the ONVIF and WS-Discovery protocol later on. So, but first, I'll start with mDNS and DNS-SD. So, multicast DNS is a zero configuration protocol that is really prevalent in IoT ecosystems. Basically, it's all about automation. And usually when you have a lot of automation, you have to sacrifice some security. So with mDNS, the idea is that it works in very similarly to DNS, but it's mostly for local networks. So whenever you plug in a device like a camera or whatever other smart device in your home system or even corporate environment, you want to automatically configure it. And mDNS is one way where the device announces itself on the network and you can automatically manage it. So a few things about mDNS. First of all, it works on UDP, uses port 5353. It's also easier to remember because of DNS using 5.3. Multicast addresses, you can see them there for IPv4 and IPv6. It uses the .local domain, so whenever you see on wireshark.local, you can easily realize this is DNS, mDNS. And there are two phases, probing and announcing, that we're going to inspect later. It works in tandem with DNS service discovery, so you almost always see these two protocols together. And DNS-SD is a way to for devices to announce what services they can provide on the network. So, for example, if there is a printer and wants to announce that I can print, you can send print jobs on this URL, on this IP address, on this port. They use that. So the records that it uses are very similar to DNS, basically the same, but the way they're used is a bit different. So you have pointer records, you have service records that have the the host name and the port on which the service is configured, and then you have the text record where you can have information such as the exact URL that for example, for printers or whatever other service. And the service record is usually also accompanied by either the A record for IPv4 or the 4A's record for IPv6. And using this triplet, the pointer service and text triplet, plus the A record, you have all the information you need on the network to communicate with that service. So let's see an example. For the probing phase, which is the first phase for whenever you plug in a device, basically what it does is that it asks if anyone else on the network provides the same service under this particular name that we want to register. So a printer, for example, there will say, does anyone else on the network have this test IPPS TCP local service? And it will send a query on the multicast address, as you can see there. Hopefully it's visible. But it will ask anyone on the network if they already have this registered. And if no one replies after a few seconds, then the printer will move on to the announcement phase, which is basically saying that, okay, since no one else has this record, has this service, I will take it for the local network, and I will establish that I have this service that you can use. And it will send an unsolicited multicast mDNS response that contains all of these newly registered records, which, as I mentioned before, will include the pointer service and text triplets, plus the A record for name resolution. So let's see an actual scenario there. Say you have a MacBook user that wants to print a document, and to make this more interesting, we assume that the system has an already pre-configured network printer named test. This is, by the way, this is on the Bonjour implementation of mDNS, which is how Apple has implemented it. And now the main flaw, the main logical flaw, because again, this isn't an implementation bug, this is a bug in the logic, in the design of the protocol, because there is a specific reason why they have done it this way, is that even if the service had been discovered in the past, it doesn't matter, because say, for example, you want, at some point the printer changes the host name or the IP address, because whenever you have, say, a corporate network, you might have, or a home network, you might have some of those changes. So because we want this flexibility of whenever the underlying host name or IP address change, we still want to be able to communicate with the same printer that provides the service called test IPP or IPPS or whatever. The mDNS and DNS-SD protocols are designed in such a way that every time we want to communicate with them, we ask them again, are you still there, or do you still have this? Do you still have on the network this service under this particular host name and port and URL? So the main flaw there is that even if in the past a printer had established its presence by going through the probing and announcement phase, we still can exploit that as an attacker on the network. And so the macOS client that wants to print the job will always be sending a new mDNS query asking where the test service is. And then, so it will send a query on the network like this, and the printer will then reply in the same way as it had done in the announcement phase by sending the triplet plus the A record and the TXT record, which also contains the URL for the printer, the printing server. So in this case, it's that one. And now the macOS client basically knows everything they need to connect to the printer and send the document. They know the instance name from the pointer record. They know the exact host name and the TCP port from the service record. They know that the host name resolves to this particular IP address on the network using the A record. And they know the exact URL to post the print jobs through the text record. So what can we do there? This is an attack called mDNS poisoning. The thing is that as far as I had tried, there wasn't anything that worked really well, so I created my own mDNS poisoner. And the attack principle is really simple. We listen as a man-in-the-middle attacker on the network. We just listen for multicast mDNS traffic on this UDP port. Since it's multicast, we can listen it without having done anything else. We don't need to do, for example, ARP cache poisoning or DNS hijacking. We just sit on the network and listen for multicast traffic. And then step number 2, the client, since we mentioned that there's this fundamental flaw that every time the client wants to print something, they need to ask again and ask again on the network to rediscover where the test printer is. So it will send an mDNS query, and then as an attacker, if we continuously send back replies on the network to poison the client's cache, that I am the printer, the network printer, and not the legitimate one. And if we can win this race condition, which is really easy to do if we have already started eliciting responses before even the client has asked, by sacrificing a bit more traffic on the network. So if we can win this race, or we just flood the network with a lot of mDNS replies, then we are basically positioned in such a way that the victim will send the print job to us, and then we can steal the document and we can forward that to the actual printer. so that the victim doesn't know anything about it. And I have a demo for that. Hopefully, I'm not sure if it's super visible, but I'll explain what's happening. So in the left part of the screen, we have two things. First of all, there's a terminal there that will run the poisoner, and on the bottom left we have an IPP server, which is just an easy way to emulate a print server. The left terminals are from the attacker. The right one is the legitimate IPP server that basically emulates a network printer. And the first part of the attack is that the first part of the video will show the legitimate user, the MacBook, that will connect to the IPP server and will send a print job. Let me see why it's doing this. All right. So you can see this is just some output there that we, as a MacBook client, we connected there. We sent the print job. Nothing has happened so far. The attack isn't really taking place yet. And now we'll start the poisoner on the on the top left. And now the MacBook client will send again another print job it will try to send it to the legitimate printer. As you can see, now we send back the replies. Nothing is happening on the right part of the screen because that's where the legitimate one is. But we can see that on the bottom left, we are the ones that get, as an attacker, the print job. And so the MacBook now has connected to us instead of the legitimate one. And then at the end, we'll have the print job there on the bottom left. So we have all we need to, steal the document. And that's basically it. And so this was just to demonstrate the fundamental flaws that are in some of those zero configuration protocols. IPv6. Few things about this is that recently on the standard, to make it more lax, whenever you read RFCs, there are these keywords that actually play more and more important role than they initially seem to. So, for example, whenever you see must, that means that whoever implements this protocol should 100% make sure that it follows this, this rule that the standard specifies. But whenever you see should, that means that it's more or less a guideline in that case. So you should do that, but even if you don't, then it's not the end of the world. So that means that it leaves some room for flexibility. And in that case, you can see some variations in how these protocols are actually implemented. And you can see that in things like even TCP or IP. And that's why, for example, whenever you do an operating system fingerprinting using Nmap, you can have all these, you can inspect all those patterns of how the different operating systems, the different TCP IP stacks reply back to you, and you can thus analyze the responses and see how these variations in the implementation can help you figure out the exact kernel version, or if the system is Windows, or some variation of OpenBSD, for example. So all of these keywords there, whenever you read an RFC or a standard, do play a role. So recently for IPv6, although IPsec was supposed to always be, be there whenever you have an IPv6 deployment, recently it became should. So that means that you might have some room for, another attack vector there. The other thing that we have seen whenever we test medical devices specifically, but you can also see it in IoT, the superset of IoT systems, is that IPv6 is often overlooked as an attack vector. So we have seen, for example, there was a medical device in the past that, although IPv4 was completely filtered by the firewall, when we tested, scanning for some ports and finding services using IPv6, everything was open. So apparently the vendor had completely overlooked that, there's also IPv6 that needs to be filtered explicitly, and there's another attack vector. The other thing is most of the attacks that we know work on the local network, like the ARP cache poisoning. There's a very similar thing on IPv6, which is the neighbor cache poisoning that works in exactly the same way. So whenever with ARP you need to find the MAC address. You don't know the MAC address to communicate on the link layer. You know the IP address, and you ask on the network who has this MAC address. The same principle is with IPv6. They just now name it neighbor discovery protocol, and it's the exact same principle. So this is a known attack. And the other thing is with ICMP redirection. This isn't as popular as ARP cache poisoning, but again, it works in the same principle that with ICMP-v6 as in ICMP-v4. So the idea there is that whenever you want to do some performance, let's say optimization in the network traffic, so you have like two routers on the same network, and you see that you want to redirect a flow of the traffic in a different router because one of them is flooded with a lot of traffic already, then you can have this special message on ICMP that says, okay, now you must redirect your, all your communication through this router. And of course, because there's no authentication there, an attacker on the network can say, okay, I'm that router, I'll redirect all the traffic through me, and it's another way to position yourself as a man in the middle. The other thing that I have to mention there is with extension headers. They're a big complex mess in IPv6. There's some really good research by some people out there on how you can abuse a lot of these extension headers to bypass access control lists, or even trigger some implementation bugs in IPv6. So let's talk about smart homes now. One of the protocols that recently has taken some popularity there is the AllJoyn. By the way, this is an interoperability protocol, so it's used for bridging different, say, smart devices between each other, and so that they have the same type of language, so to say, that to speak with each other. So you have like a smart light bulb on your network, and you want that to be able to talk with your hub. Then AllJoyn comes to the picture, and we have seen that now recently even be supported by Windows 10. So if you see, if you open your task manager there, you can see that AllJoyn service is probably running. And there are not a lot of things there. So recently they updated their security requirements. The previous version was a lot more insecure. But there are still some risks there as far as we have seen. So for example, you can, some parts of the headers actually for AllJoyn are unencrypted. So you can see some information about who talks with whom there. There's some sessionless signals which are used again for the same type of principle of zero configuration that we previously mentioned. So for example, for discovery and announcement of the services, you have no authentication, no encryption, and again, you can do these sorts of attacks there. Also deadlocks, because you have a lot of parallel method calls, so it's a really complex protocol. Also, it runs on, it's based on XML, so there's a lot of room for fuzzing there. And multi-point sessions, you can spoof some identities there because of the, whenever you have a group, because you can form small groups there, you have the same symmetric group key that is used by all members of the same group, but then that leaves a lot of room for spoofing any participant in that group. So IoT sensors, some of the things we've seen there while testing them in especially healthcare environments is that you can have some debug services there where you can, connect to them without any authentication. You can do all sorts of, lack of input sanitization is one of the most common bugs there. So just some small fuzzing or even just cutting the dev view random to that service using ncat or netcat can just make it crash. So it's usually as simple as that. Replay attacks, of course. You can just replay traffic and fool a sensor into, say, thinking that the temperature in that room is X degrees, while it's not really the case. One of the other things we have seen is that many people try to reinvent the wheel with encryption. They might think that they're smarter than the best cryptographers out there, and they can re-implement their own custom encryption algorithm. So one of the things, for example, we've seen is that you might have an XOR operation with a fixed byte value, and they call this encryption. And whenever there's an associated mobile application, then the permissions it asks are just too much. So they might ask to, you might wonder, why as an application that does a very simple thing communicating with the IoT sensor, why do you need to have access to my camera? And speaking of cameras, IP cameras are another thing that we test regularly. An example vulnerability that we had found a while ago was that after we downloaded the firmware and analyzed it, we saw that by inspecting the file system that there were some, in some configuration files, you could see the skip auth keyword next to some specific URLs, which made us wonder, why do they have this? And if you accessed those URLs, then you could access them without authentication, as the keyword implies. And one of them, you could take just camera snapshots, for example. And this was a security IP camera, supposedly. And one of the protocols that is used there for, again, automating a lot of the deployment is ONVIF, which is an interoperability protocol, so that all the different vendors of IP cameras can speak the same language. And there's one particular subset of it called WS-Discovery, which is the same principle has the same principles as the mDNS and DNS-SD. So what it does is that whenever you, say, plug in a network camera on your network, it announces its presence. And the reason that it does that is that whenever you have a corporate environment with lots of different security cameras, you need an easy way to manage them. So you want to, for example, have all the video feed of all the different cameras be in a centralized server. And so there is this WS-Discovery protocol that whenever you plug in a camera, it says, okay, here I am, I'm a new camera. You can connect to me in this IP address. And if you know the right credentials there from the IP camera server software, then you can connect to it and associate each other with, and then you can just access the camera through that server instead of manually going to each of those cameras and accessing their web portal, for example, which when you have hundreds or thousands of cameras in a hospital, for example, or just a big enterprise, it's not scalable. And WS-Discovery then works, again, with no authentication. So you just send a multicast probe saying that, here I am, here's the camera. And the way this works, so back to this schematic, which is from the standard, there are two main probes that are involved in the beginning of the process. The probe multicast and then the PM, which is probe match. And the first one is sent on the multicast address, the one you see there, and it's just SOAP queries over UDP. Client in this case is the server. So the server is asking, is there anything on the network that needs to associate with me? And the target service then is the camera that recently entered the network, and it only needs to send a probe match reply, and the only requirement there is that this particular field, the envelope header relates to, must have just the value of the message ID property from the probe that the server just sent previously. So there's no authentication. Basically, you can just parse that ID, and then you can just craft a new message, probe match, that can be sent to the server and announce that this is a legitimate camera. And I have demonstrated an example here against an open source software called Camlytics that is basically a camera management server that speaks ONVIF and WS-Discovery. So the idea there is that you can basically create fake cameras, rogue cameras on the network. And because whenever the server will ask, is there any camera here, you can just send a spoofed reply using this protocol. And the attacks that you can do there is that, first of all, since we're talking about XML, because it's SOAP queries, you can easily create a lot of memory corruption, trigger a lot of memory corruption vulnerabilities. And we have seen a lot of these kinds of stuff in even enterprise-grade camera servers. So we had a simple Python script where we just replied to this probe request of the server, and we sent a specially crafted XML message that then made the server crash. And you can, of course, refine that even to a remote code execution exploit. Then the other thing you can do is that you can impersonate a real camera. So if you can, capture some of the traffic, or if you have some awareness of the network around you and what type of cameras they run, they have there already, you can basically create a message, an XML message that has very similar attributes to the ones that are expected to be on the network. So whenever the operator sees that in the window that lists all the new cameras on the network, he will say, okay, yeah, here's a camera that I expect to be because it's from vendor X, that you can easily, again, spoof in that message that you previously sent. And you can, of course, if they expect to see a real camera there, you can either create a denial of service on the real camera or just win the race against it. So whenever the server sends, okay, is there a new camera here? If you win the race against the real camera, that will send the legitimate probe match reply, and you send it first, then the real camera will not be included in the list, but your fake camera will be included in the server list. And by that, you can replace the camera with a fake one. And then, of course, you can do all sorts of stuff like sending artificial video input to the server. And also, the other thing you can do is that since the server will then attempt to authenticate to that camera, because it expects to use a certain set of credentials, you can also capture them some of the times, depending on what kind of authentication they use. And of course, some of those credentials are, whenever you have them in, since a lot of the times they use the same ones, you can then reuse them in other cameras and also exploit those. You can also send malicious links to the operator inside the match probe, the fake query, the fake response to the query. And the other thing that is there in the WS-Discovery standard is that there's this concept called discovery proxies. And these are basically web servers that act as pivoting points so that you can use WS-Discovery over even the internet. So this allows for the attack vector to be extended to even remotely, although you would otherwise only be able to do that locally on the network. RTSP, RTP, and RTCP. So again, as an extension of the work on the IP cameras, whenever those cameras send video feed to the server, they usually do this over using these three protocols. The first one is the controlling protocol, so it sets up the session and then uses some VHS-style commands like play, stop, forward, or and so on. The RTP is the main data transmission protocol for the video, and then RTCP is just for out-of-band statistics on the performance and so on. The main problem with all of those is that, and they are still used by all IP cameras out there, is that they are unencrypted, they don't have any integrity checking or message authentication, and the best alternatives that are more secure, SRTP and SRTCP, we have actually not seen them anywhere being deployed. Although there are standards, some of the IP cameras don't even support them, or the management software might not support them. But basically, we haven't seen them anywhere. And one of the attacks that we wanted to demonstrate there is just the simple thing of being able to play back the video whenever you capture the traffic, just to demonstrate to whoever is a stakeholder in the company that you have to do something about this. Just run it over TLS or do some other workaround, because just having unencrypted video being streamed in your network is really bad for any man-in-the-middle attacker. They can just capture the traffic and then play back the video. And then there was just, how do we do this? The answer is really simple. We just need the session description protocol packet that is sent, that is in there in the traffic, especially in the beginning of the RTSP session establishment. then we just use these three tools. There were some other automated tools that are supposed to do that, but they never worked for us. So we just use a combination of RTP tools, FFmpeg, and just Wireshark for capturing the traffic. We just need to export the buckets from the SDP portion of the RTSP, modify a few things, and then just use a combination of FFmpeg and RTP play to decode all the traffic into a playable video. And then we just play it with any video player. And the last and probably most interesting part is the IOMT environment. Some of the interesting things that we have tested there. So we have tested all sorts of medical devices, from infusion pumps to pacemakers to surgical robots to heart rate monitors. And there are a lot of attack vectors everywhere. For example, with implantable devices, recently there's been this trend of having home monitoring devices where you have a patient that has a pacemaker implanted in them, and then this device communicates with another system that is installed on the patient's home. They talk over a wireless protocol, and then say once per day, the pacemaker sends some diagnostic data to the home monitor, which then sends that to the cloud. The idea there is that you want the physician, the doctor actually monitoring the patient's health, to be able to see and diagnose on time if there's any anomalies in, say, the heart rate or if there's any other complication that would require the patient to come, to the hospital and be checked more thoroughly. And by sending those data to the cloud, the physician can then use the web portal and can see, okay, yeah, everything's good, or if there's an anomaly in the diagnostical data coming from the pacemaker, that so we need to do something about it. But of course, there are a lot of attack vectors depending on how the home monitoring device connects to the network, if it does this over 4G, or if it does this over a landline, or if it does this by connected to your home router using Wi-Fi. And because that allows the attacker to also, and a potential attacker to compromise the home network of the patient, and then use the home monitoring device as a pivoting point to interact with a pacemaker using, this wireless protocol that they use. So some of the common vulnerabilities that we see in medical devices, one of our main problems is hard-coded credentials. Whenever those get leaked, there's no easy way to configure the system to change them. So they are usually, we've seen a lot of encryption keys, sensitive secrets, sensitive passwords for authenticating the medical device to authenticate with, say, a controlling server, and those are embedded in the binaries because they think it's a good idea to have them there. And of course, then there's no easy way. There's no configuration file to easily change them. They have to issue a patch, which, imagine the case where that medical device is, say, a pacemaker. It's a big deal having to call the patient at the doctor's office to say, I want to apply a firmware patch on your pacemaker, just because the vendor had forgotten some hard-coded credentials that can potentially be abused to do something bad to your pacemaker. Default passwords, lots of medical devices, they do not integrate with centralized servers, so there's a lot of insecurities there. For example, using weak credentials, or just shipping the systems with default credentials and there's no documentation there that can raise awareness to the technicians deploying these devices that you need to change those whenever they get installed on the healthcare network. Then whenever there's a web application, you can do all sorts of injections, SQL injections, cross-site scripting, all sorts of stuff that you see in common software. Patching is a really big problem because you cannot just, with medical devices, whenever they reach by the time they reach the market, they have to usually go through FDA approval, which means that they usually come outdated, and then because you cannot just apply patches on an infusion pump, let's say, by not first going through a lot of rigorous testing, the whole patch management is a big problem. So the other day I was talking with an engineer of a vendor that make blood analyzers, and they were telling me that, you know what, we know that there's all of these vulnerabilities, and we try to patch those devices fast, but the problem is that whenever we make any slight change on the firmware or software of those devices, we have to do about 3 months of testing, so that you don't have a blood analyzer, say, because of a floating point error caused by the new patch, can make the blood analyzer diagnose you for, say you have hepatitis or something else, while in fact you don't. So there's a lot of accountability there to keep the device functioning as it should, and those new patches that are applied do not make anything go wrong. So that's why we see a lot of outdated and devices out there. And another example was that with WannaCry, a year and a half ago almost, the national healthcare system of the UK was, completely out for many days. Surgeries had to be cancelled, appointments had to be remade, because there was, this ransomware spreading, and a lot of those devices having SMB exposed could not be patched on time, because vendors were saying, okay, we need to still test a lot of things, even if you want to disable SMB, because something might go wrong, and they don't want this, accountability. And I'm not sure how much time we have. I'll jump straight to some of the interesting vulnerabilities. One of my favorites was, although it wasn't a high-risk finding, with some password generation entropy that was reduced because of the fact that they hadn't done binary to text encoding first, and they just did UTF encoding. So the passwords that were generated by both the client and the server were not as secure as were not as random as they thought they were, because of this simple error. And because it was both implementing the client and the server, they could still talk with each other, but the idea there is that you can probably predict some of those passwords. The other problem is that with medical devices, we've seen network services that could crash and make the service, the whole system, the whole medical device reboot by just doing a simple Nmap service scanning. So we just run, Nmap minus SV against those devices, and just because Nmap at some point tries some specially crafted probes with the hope of eliciting some reply from the service and identify that kind of service, the device didn't properly do input sanitization and just, was bricked. And since we don't have a lot of time, I still want to say a few things about DICOM. DICOM is a healthcare protocol that's used for imaging. It's both a file and a network protocol. So it's you have a DICOM format where you can have diagnostic information, a lot of metadata about the patient, plus the images that can be really big in some cases of CT scanners. And you can have all sorts of diagnostic images there, from MRIs, X-ray machines, CT scanners, and all such things. But there's also a network part to the DICOM, and it's usually implemented by this kind of picture archiving software called PAX servers. The problem there is that there's no authentication, no encryption, no nothing. So recently an Israeli company demonstrated an attack where, as a man in the middle, you could just sit on the healthcare network and you could monitor for DICOM traffic. You could alter some of those images that get transferred, and you could add or remove cancerous nodes on the images. So that means that whenever the PAX system was sending, the medical device was sending to the PAX system, which is the like the server component that all the diagnostic information will be stored, you could falsify the diagnostic data that would then be used by the doctors to make the diagnosis. So this was just a demonstration that because of the fact that this protocol is usually deployed without any encryption, you can do some really serious attacks with real-world implications. And one of the problems there that we had also demonstrated at the DEF CON Biohacking Village last year at the Capture the Flag was that the application entity titles that are the only thing that are used by PAX servers to as a sort of authentication, they're really easily brute forceable because you can first find there are two parts to it. The target application entity title that you can. I have actually written an NCRAC module for it, which will try to do a dictionary attack against this. And then there's this you can do against this commands associate DICOM command that is used for DICOM clients to initially associate themselves. So in that case, medical devices that want to speak to a PAX server, they will send an associate command, and they will only need the correct application entity title, which is usually also the host name of the PAX server, and you can easily brute force that. And then as a second step, as long as you have found the correct application entity title, you only need to find the correct client the allowed client application entity title, which is, again, it might be a host name, it might be something easily brute forceable. You can do that with a simple, Python script. And using these two steps, you can easily find out the correct pair and of credentials. And using that, you can just start extracting protected health information, which means patient-sensitive information. And one of the last things, recently there was this research about malware in DICOM, so embedding a portable executable file inside the DICOM file, which is a really serious infection vector, because whenever you have an infected DICOM file, then you can't just have the anti-malware solutions, endpoint solutions, just quarantine the file, because since it contains patient-sensitive information, you still need to have that file intact. You need to. You can't just delete the file. You don't have an easy way to disinfect it. So this opens a whole new can of worms about attack vectors by using this hybrid PE DICOM file. And this last slide just have a list of resources about all this stuff we talked. And yeah, this is basically it. Thank you.